Okay, so what if we wanted to define the arc length as an actual function? So if we had a continuous curve, so let's think about this graphically, what this would mean. If I had a continuous curve, let's call this the t-axis actually, because I'm going to use x as my variable in the new function. And so here we've got y equals f of t, and we're on some interval from a to b, and it's a continuous curve. And if we wanted to think of x as some value between a and b, some value on the interval from a to b, then we could define this new function, s of x. So here we go. S of x is actually going to be this new function that we're going to call the integral from a to x, which means that we're actually defining it. The variable piece of it is one of the bounds of the integral. So what that's saying now is find the actual length of the curve from a to x, and then notice there you have our arc length integral. So that would be the actual length of this curve, trying to trace it here in red and bold. That would be what this function right here, s of x, is representing. It's representing the actual length of the curve. Sorry, my line got a little squiggly there. Let's do that again. That would be representing the length of the curve from the initial point, a, f of a, to the new point, x, f of x. So, and x again is variable, so this can change. This guy can move up and down on that interval from a to b, giving us different arc lengths. Okay, so that's our arc length function. We'll do an example of that in just a second, but that does actually give us sort of an interesting interpretation if we apply the fundamental theorem of calculus to that new function that we've just defined. If we take the derivative of it, we end up finding that s prime of x is equal to that square root of 1 plus f prime of x squared, just applying fundamental theorem of calculus from Calc 1. And just with a little manipulation, I went for the Leibniz notation here so we could talk about the differentials. And if we apply a little bit of manipulation there, we get ds, this new differential ds, is equal to the square root of 1 plus dy dx squared dx. And then just a little bit of algebraic manipulation. If we pull that dx into the root as dx squared, we would get this nice little square root function, square root both sides, and we end up finding this relationship between ds squared equaling dx squared plus dy squared. And it actually gives us a pretty cool representation if we jump over to the function and we look at this little triangle, and you can see the relationship between those differentials, dx, dy, and ds on the triangle versus the actual curve. And I noticed here on this particular graph, I pulled this out of the Stewart book, but dx is actually equal to delta x, the change in x. And you can see that that is not true. The differential dy is not exactly equal to delta y being the change in the function. Dy is this slightly, in this particular graph, this slightly larger value, and then ds right here is the hypotenuse of that triangle. So it does give us interesting interpretation and something that we can utilize in a formula that we're going to look at in the next section. So worth kind of keeping that little piece in mind. But I would like to do an example of that actual arc length function. So if we go down here, let's see if I can get this all on the screen. There we go. And so let's look at this particular example. If we wanted to find the arc length of some function, let's call, or let's look at the function y equals the natural log of the sine of x, but because of our domain for the natural log, let's look only at it when x is between 0 and pi, and we'll have a starting point for our new arc length function of x equals pi over 2, y equals 0. So this is going to be our starting point. We could think of that as p naught. So that'll be our starting point of our new arc length function. So I actually jumped over to Desmos before making this recording, and I grabbed a little graph of what that actual curve looks like from 0 to pi, and so we can see it right there. And right here in the center, looks like on the x-axis that didn't come over, but that's pi over 2. So if we wanted to find this arc length function, we're going to define the arc length function, or we defined the arc length function as the function s of x. So this is going to be s of x equals the integral from, well, where we started was pi over 2. So pi over 2 to some, now it's a variable bound, to some x. So starting at pi over 2 to some x. And we're going to look at this as the square root of 1 plus, well, we actually have to consider this. Let's pause for just a second here. And underneath here, let's think y equals ln of the sine of t. And let's think, what would actually dy dt be? Okay, because we need to plug that in here. So this needs to be dy dt squared, because we're integrating with respect to t. Our x variable is now in the bound of the integral. So dy dt, if we take the derivative here, this would be 1 over the sine of t times the cosine of t. But that becomes, oh, look at that. Cosine of t over sine of t, that's actually the cotangent of t. I'll put a parenthesis there since it looks like two t's. And then if we take 1 plus, again, I just want to do a little simplification. I think you've seen this in my examples so far. I like to do the simplification outside the integral. So 1 plus, we're actually going to end up squaring, so I can get rid of that parenthesis, cotangent squared of t. So 1 plus the cotangent squared of t. But that is actually the cosecant squared of t. So just applying some trig integrals here. And now let's just go ahead, go back to our definition there of our arc length function. And now plugging that in for this particular function, s of x is going to be equal to the integral from pi over 2 to x of the square root of the cosecant squared of t dt. Now, before I scroll up, just wanted to make a little note here that we are only looking at this function from x equals 0 to x equals pi. So keep that in mind, because when I take this square root right here, this ends up being equal to the integral from pi over 2 to x of the absolute value of the cosecant squared of t dt. But because we're only looking at the cosecant, I'm sorry, just the cosecant, the absolute value of just the cosecant when I take the square root, just the absolute value of the cosecant of t. But since we're only looking at it from 0 to pi, that is actually a positive function from 0 to pi. So again, remember, cosecant is defined as 1 over the sine of t, and sine is positive from 0 to pi. So kind of keeping in mind that on that restricted domain there that we can drop the absolute value when we take the square root. All right, so then this ends up being equal to, well, the integral of the cosecant, we'll write that without the absolute values, so pi over 2 to x of just the cosecant of t dt. And the cosecant of t is actually, if we did the proof of the integral of the secant in class. We didn't do the cosecant, but it does turn out that the integral of the cosecant is real similar proof. So the natural log of the absolute value of the cosecant of t minus the cotangent of t. And we are evaluating that from our bounds, and we do have a variable bound, pi over 2 to x. And so this ends up being, when we plug those in, we get the natural log of the absolute value of the cosecant of x minus the cotangent of x minus the natural log of the absolute value of the cosecant of pi over 2 minus the cotangent of pi over 2. And the cosecant of pi over 2 is 1, and the cotangent is 0, and so we have the natural log of the absolute value of the cosecant of x minus the cotangent of x. And then this piece becomes just the natural log of 1. But the natural log of 1 is 0, and we find that our actual arc length function, s of x, is equal to the natural log of the absolute value of the cosecant of x minus the cotangent of x. And just as a reminder, what this is actually representing, it's a function. So this represents the actual length of the curve So this is the length of the curve of y equals the natural log of the sine of t from x equals, our starting point for x was pi over 2. So from x equals pi over 2 to x on the interval from pi over 2 to pi. All right, so that's what that actually represents. We now have a function, so I could plug in any x that I wanted on that interval, and it would tell me what the actual length of that curve is. So we can use that arc length function. So rather than doing it for a specific value, we just turned that integral into a function by changing the bound, and that gave us a function that represents arc length. All right.